All right, so this is obviously the sample test for Unit 2. Number 1, the directions say find the general solution to the differential equation. So for this one, you can technically separate the variables. All that would mean here is moving the dx over to the other side first, and then you're integrating both sides, but the left side obviously with respect to y, and the right side then with respect to x. But all this really boils down to, really, because the left side is just going to be y. So on the right side, the way we do that is with u substitution. So this one will work by letting u equal sine, because if you think of this as a bubble squared, and inside the bubble is sine, normally you let u equal whatever the inside is. So when you do that, and that part of the substitution, you end up with the u in for sine, but then when you also replace the dx with this du, well, you're really replacing it with du over cosine. So this cosine cancels when you do this substitution. And then you're freed up to actually integrate just with basic power rules. And don't forget your plus c, and also don't forget to plug back in for u. And so here's your final answer for number 1. Number 2, same sort of intro about, is this technically separation of variables? Sure, but all you really end up doing is integrating on the right side here. And it helps to rewrite both of these first with a little bit of algebra. Haven't actually taken the integral yet of both sides. See, I'm not even, I think, taking the not even like doing a step of probably moving the dx to the other side. But now you're okay to integrate over here, but what happens when you integrate 1 over x, or essentially x to the negative 1? You get the natural log of the absolute value of x. So I guess I kind of did. I did take it actually in a step, move the dx to the other side. And so don't forget your plus c. And that will do it. Unless you want to write this as as 1 over x. That might be a bit better, most people would argue, to have that written instead of having a negative power, to saying 1, well, with the negative out here, of course, but negative 1 over x minus the natural log of absolute value of x plus c. Then we get into like the same sort of thing. So the progression here is pretty obvious. We're doing essentially the same thing, but now we have an initial condition, which means you'll be able to figure out what your c value actually is specifically. Or particularly, we're finding now the particular solution. So again, technically the dx would move over here, but then, and on the left side, when we integrate, will just be y, obviously. And how do we do that? By letting u equal x squared. And then when we let dx get replaced with this, with du over 2x, that this x cancels, and we also have like a 1/2 involved when we do this substitution. So I'm kind of been skipping some baby steps of plugging in whatever dx equals and then whatever cancels and everything, but this would be the result of plugging in for the dx and for x squared, But now it's time to integrate, which now the integral becomes a lot easier. And so don't forget your plus c, and to plug back in for u. But now we're able to plug in u for x and 3/2 for y, and end up with a c value of 1, which means you can put that into your final answer, which is that. Again, always feel free to pause the video if I clicked ahead too fast here. Same sort of thing. We're just solving a differential equation. There's really no earth-shattering separation, that is needed. So we just integrate all this, and this is what we get. 4x to the 4th over 4. I'm assuming you don't need me to go through old things like, integrating all these terms and how it's done, but this should remind you pretty good. And this is the cleanup. And now would be time to plug in -1 for x and 2 for y. And so, yeah, -1 to the 4th power is +1. This ends up being a -1, which means times that, -2 will be a +2, yada, yada, yada. We end up with c equals -3, which means our final, and you would plug it back into here. Construct a slope field. It looks like I labeled each one. You don't need to do that. I mean, if it helps you, then go for it. But basically, for example, here at this point, the x equals 0 and y equals 0. So if you plugged in 0 for x and 0 for y, looks like your dy dx, your slope, dy dx is slope, would equal 0 at this spot. So that's why it's a little line segment with it's horizontal. It's got a slope of 0. Over here, like 1, 1, so x is 1 and y is 1. So you'd have 1 minus 2 times 1 for dy dx at that spot. So you'd end up with an overall dy dx of -1, which means, like down 1 over 1, like this kind of downhill slope, like perfectly diagonal. For example, over here at -1, 2. So this would be like -1 -2 oops, sorry, I had to pause the video really quick. Someone was coming in the house. I thought the dog was going to start barking up a storm. So where was I? Just with this point, I think. So, I think you probably get the picture by now. But for this point, this is -1, 2. And so if you plugged in -1 for x and +2 for y, it would end up as like -1 minus 4. And so that's where you get a dy dx, a slope of -5. So that's getting pretty steep in a downhill. Remember, negative slope means downhill. Positive slope means uphill, like +2, +1, +1, +3 is a little steeper than +2. No big stress over making these look like amazing and like really, 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 really accurate, perfect slopes of 3 or -2 or whatever. This one's a little bit easier because, you can almost have all of these points are going to make the same dy dx slope because the slope is really just 2 times whatever the x coordinate is. The y coordinate doesn't even matter. So for x equals 0, 2 times 0, the slope is always 0. For x equals 1, the slope is always positive 2. And for all these points where x is negative 1, 2 times negative 1 is negative 2. So pause the video if needed, but I'm moving on to Euler's method. And at least these days, the year is now 2025 on planet Earth. But, you know, at these days, what I do is I have it set up like this, to where you need to kind of figure out all these change in y's kind of manually, but then you can use technology, and we probably have a little formula into your graphing calculator that'll let you skip ahead and just get like the final answer. Like for this one, if you just threw all this stuff into your calculator, which it should be the program. I mean, again, I'm going off of what we're doing these days in the year 2025. But when you plug in x for your calculator program, x and y are what you're kind of starting at. So it'd be like x equals 0 and y equals 1. And then you'd be plugging in for t, which is like your terminating x. You know, you're plugging in 2 because you're trying to go all the way to x equals 2. So this would be your t value, and then your c value on your calculator program that we've done in class. The c is the change in x. You know, and then of course, don't forget this. You'd have to type in this differential equation in for your y1, and you know, you like in the y equals, hit the y equals button, and you have to put this in there. But so that's all just to get this like final answer of about 0.764. So the stuff by hand, just remember that the change in y, all you got to do is like dy dx times delta x. This will be equal to dy dx times delta x. I don't know, I did write out some work here. Good. So this is the dy dx part, and you got to use your current x and y values. So at the moment, x is 0, y is 1, and that's what gets plugged into here. And then the good news is your delta x is always just going to be 0.1. Okay? And these, I guess I already have these in here for you. You're welcome. But these are not a mystery even from the beginning, because you know that the change in x is 0.1. So if you're starting at 0, then the next one's going to be 0.1 comma something, and then the point after that is going to be 0.2 comma something, and then all the way to 2 comma something. So this is, hey look, just another reminder, this is not your new y coordinate, it's your change in y. This is, I mean, you know this is change in y. Just don't fall asleep here and at the wheel and and act like this is your new y value. It's your change in y, which is, so goes from 1 to 0.8. And then you just kind of rinse and repeat. You do the same thing, but now your x and y values are different. So when that plugs into dy dx, you get something different. And so this change in y is that, negative 0.15. So you would add that technically. It's a negative, so you're going to add it technically and get that, rinse and repeat, and that's all you got to do for like the manual work, because your final answer you get from your calculator. Same thing here, and I think the program you're using should account for a negative delta x, so you don't need to like change any code or anything, like you're fine. But you do need to go back into your y equals and change the differential equation in your y1 equals. And so same thing. Hopefully you tried all this before looking at the video. If you come to the video beforehand, you're maybe desperate, I don't know. But You should get like negative 0.25 for that change in y, negative 0.235, and then negative 0.22075. And then your calculator, if you plug everything correctly, x, y, your t value is right here. Your c value is now negative 0.05, so that's what you should get. Then we get into some differential equations where, you know, some real separation is necessary. So for number 9, you'd have to move the y, like you'd multiply the y over to the dy. You'd multiply the dx over to the right side with the 2x. Then you can integrate, and on the left side you get that, and on the right side you get, like, you know, 2x squared over 2, but the 2's are going to cancel, so you're just left with x squared, right? Plus c. Oh, wow. I'm trying to remember what I have here. Is this just because of finding c values at different times? So don't get confused by all this, like, or this, or this, or this. I think this is just going to be, let's see here. Well, let's maybe look at this first. So, yep, if you find C right now, or maybe it's just different ways to have your final answer, maybe I'm wrong about why there's all these extra answers, you know, alternative answers. Maybe it's just how you would, like, write your final, like whether you solve for y or not or something, you know, get y by itself, whatever. But plugging in your initial values, you end up with c equals 1. So, you know, you plug it back in for c and you get this. Maybe what's here is if you actually tried to, like, get y by itself, you know. Yeah, I'm not going to get too picky about final answers. You know, you could move the x squared over to the other side, basically because this is kind of like, you know, a circle or a hyperbola or an ellipse or something, you know, where now it looks like in this sort of standard form for the equation, you know, if you're talking about like a hyperbola or an ellipse or something. Is this when I actually get y by... So you could have stopped here, whatever. This is if you get like all the way to having y by itself. I'll accept any of that. And then this one, look, remember, you got to be ready for this kind of trick. Like, how can you technically get these variables separated? Well, the first thing you have to do is apply a little old school algebra, you know. When do you add powers? When it's almost like reverse engineering that whole thing with, like, when do you add powers? And now you can separate the variables. Still haven't integrated. Do you see how this is a pretty good necessary rewrite? So I still haven't integrated. But now I have. So let's see here. You could kind of write this in. And listen to this closely. Integrating the left side. Integrating the left side is some u substitution. Okay? You don't really need to write out any u substitution on the right side. It's most people would say, like, nah, but on the left side, you know, this is technically u substitution, right? Doing u substitution on the right side would be kind of pointless. It doesn't make any, like, change at all. I mean, that's what I was kind of meaning. But on the left side, you know, you would technically let u equal negative y, right? You would let u technically equal negative y. And then when you go through all of that stuff, that whole song and dance, you end up with this negative now in play. So that's what's going on with this negative. It's because of the whole rigmarole of u substitution, okay? And, then we get to here, and then it's a matter of solving for C. And kind of like the last problem, how far do you need to go for like your final answer? Because once you know that is what C equals, well, that's a nice C value right there. But hey, so that's fine. Or if you want to, then like divide both sides by -1. But if you actually want to solve for y, like all the way USA, but that's fine. I'm not going to get hung up on, how far you're going for like a proper final answer. Just worried about the separation of variables and the initial condition stuff. Then we get into exponential growth and decay and restricted growth and logistic growth. Maybe this is where I'll mention and remind you that you're going to get a formula sheet on the test. Here's what it's going to look like, at least in the year 2025. So it'll kind of tell you this stuff, like that's included. So knowing that the rate of growth or decay is proportional to the amount present, that means we do, technically this differential equation, but really this formula. And if the problem says it's proportional to a difference, or it kind of refers to that, more on that in a second. Or if it says, proportional both to the amount present and to a difference between the amount present and a fixed constant, or it basically says that in so many words, like in other words, right? Then you know to use this formula. I think, and we can double check as we go through like these sample test problems, but what you might have to memorize, like what you might have to just know that's not on this formula sheet is, ready? You're going to probably have to know that half-life stuff or like carbon dating stuff, that's this situation, exponential growth and decay. So if the problem is about half-life, it might not actually give you any other clues that this is the formula that you use. So you just have to know that half-life or carbon dating is this situation. And you also might have to just know, I guess what we'll see here, I'm just kind of going on, I think that you have to know that like Newton's law of cooling, so anything where something is like cooling down in temperature or heating up in temperature, that would be this restricted growth situation. And it might not mention the types of words like this that would give it away otherwise. So let's see. This one, the charcoal from a tree killed in the volcanic eruption that formed Crater Lake in Oregon, contained 44.5% of the carbon found in living matter, knowing that the half-life of carbon 14, to be 5,700 years. About how old is Crater Lake? See what? There you go. You have to kind of know that this is the formula up here that you're doing. So in this problem, which I hope you're trying all this first, hope you've had that opportunity. Unless you can remember the K value for carbon dating, like this, whenever the half-life is that, which it is, you're going to end up with the same K value. So if you happen to have that K value memorized, cool, good bully for you. But first thing you got to do is do this whole like, well, okay, so if you end up with like half the amount after that many, for that T value, you can end up solving for K. The Y initials cancel out. You take the natural log of both sides, and then you solve for K. But yeah, again, fun fact, like you're always going to get that K value for carbon dating. And then once you know your K, now you can figure out, let's see, knowing that about how old is Crater Lake. So that would be when 44.5% is still there, okay? That's important because what you put over here for like your Y value is what's still there, not what's decayed, what is still present. So that's what the problem is saying, that it still contains this much. So so again, like a lot of this is like repeats itself in these problems, right? The Y initials cancel, take the natural log of both sides, yada yada yada. And that's number 11. Number 12, suppose a nasty rumor. Let me get this ready. Suppose a nasty rumor is spreading through Fort LaBeouf High School at a rate proportional both to the number of students who have already heard it and to the number who haven't. So those words right there should direct you to this formula, logistic growth. Okay, but remember the trick. You have to basically, like the way you start off is by plugging in 0 for t. So it looks like over here, I am calling, and you're allowed to do this, 4 days ago. 4 days ago, I am calling time equals 0. It's very important you define something as time 0 so you can kind of get some solving done. Like, so we're going to figure out that, you know, we can say C equals 4 if we're calling this times 0. Okay? And so as of today, 480 people have heard it. So that's the next thing you do. And so today, that would mean that t equals 4. 4 days ago was 0. So today is t equals 4. That allows you to figure out k. All right? And that's the k value you should get. That's a 3,000 right there, obviously. So your k value is negative. So when you go ahead and try to figure out, okay, what about 2 days from today, which would need to be defined as like t equals 6 right here. Ooh, look at me. I just kind of wrote, you know, negative k right here. And if you kind of remember, wait, 750, 3,000. So 750 divided by 3,000, so that, wait a minute here. K is that. Okay. Because of the 6. Oh yeah, so we're factoring in the 6. Duh. So like 6 times 750, and that's going to kind of reduce with this 3,000, or technically like negative 3,000, if you could say. And all that ends up being just like 3/2. So bottom line, final answer is this. This many people. Number 13. Okay, We're getting there. We're getting there. So here we have the actual words for this kind of decay where it says proportional to the quantity present. So that directs you to this formula, and so it takes this many years for 75% to decay, which means this much is left. So this goes in for T, and then we end up with getting to here. Keep in mind, I haven't mentioned this on this video yet, but 75%'s gone. You can do this whole thing where Y initials here, and then this is like 25% of whatever that is. You could also just come up with like some guinea pig numbers that make sense with 75% being gone and like 25% being present at that time, but like whatever, some starting amount, like you could put like 100 right here, like 100 100 whatever, 100 nuclei of it, I don't know, but or 100 grams, you could have like 100 here for like 100 grams, and over here you could have 25, which would be remaining after this many years. But either way, you're going to end up with that number right there, and then you do the natural log of both sides, get your K value, and now you can answer this question about, so like what would T equal for half-life? So again, like so many of the same steps over and over again, and you should end up with 24,100 years is that half-life, okay? After 100,000 years, so I guess you just got to plug in 100,000 in for T and 500 if that was the original amount. Now just crunch all that, and that one's kind of easy. Should get 28.176 grams. And the last question for the sample test. If a hard-boiled egg, which starts at that temperature, is put in a pan under that temperature, water to cool after 5 minutes, the egg's temperature is found to be 40 degrees Celsius. Okay. So again, like I called it, didn't I? So you just have to know that it's one of these formulas. And so if it's cooling off, then it's going to be that one because the temperature is decreasing. So, all right. So once again, you kind of have to force there to be, I think, a times 0. So we're going to call basically, the fact that originally it was 96 degrees. So at 96 degrees, that's the starting time. That time equals 0. And remember, this A value is the fixed amount, like the fixed steady temperature that's kind of having an impact and changing the temperature of the egg. So that's why the 18 goes right there. And with plugging in 0, remember, that allows us to solve for C. Remember, e to the 0 is just 1. So, and now we can do the whole thing where, like, after 5 minutes, okay, so at 5 minutes, it's now 40, and we now know we can plug in that for C. That allows us to find K, right? And remember, there technically is a negative here with the K. And now we can, phase 3, we can finally answer this question now that we know C and now that we know K. How long will it take? So we've got to figure out T for the egg to reach 20 degrees. So we plug in 20 right there. Everything else, we now know K. Notice how I was able to just kind of cancel the negatives because there's a negative here baked into the cake. And then this negative in for k, there'll be no more negative for me to need to write, you know. What do I got to do here? If I want to properly solve this, I have to move the 18 over by subtracting it, then divide both sides by 78 to get that. So subtract 18 and then divide both sides by 78. Only then would it be valid to take the natural log of both sides. So I can, you know, get to here. Now it's just solving for t by, you know, I know it's ugly, but it's just old school algebra, like getting t by itself. You get this pretty looking thing, and that can approximate to about 14.473 minutes. Pause if you need to. What was the temperature of the egg after 3 minutes? I guess that just means we're plugging in 3 for t and throwing all that into your calculator to get that. Final answer, 54.500 degrees. Alrighty. So that does it for the sample test to get you ready for the real test.